All right, in this video, we take a look at some concepts involving motion, and we look at it through a calculus lens. So just a couple of terms we want to get straight before we do a problem. First, S of t is typically the notation for a position function, v of t the velocity function, and a of t the acceleration function. The term displacement is a change in position. For those who take physics, you'll recognize the triangle as meaning change. So the displacement happens over an interval, in this case a to b. The change in position is s of b minus s of a. It'll have sign, so if you're moving rightward and leftward, then a negative displacement means that you were displaced in the negative direction or the leftward direction, and a positive one means you're displaced in the positive direction. In other words, you're to the right of where you started. Distance traveled we'll see later, but it's the sum of the absolute values of the distances between turning points. That just reminds you to keep in just keep in mind that position has a sign, and if you just start adding changes in position, you can cancel those distances out. But of course, total distance traveled, in that case, we want to count every distance as positive. We have average velocity, which is a change in position over a change in time. Notice the average velocity formula does not involve the velocity function, and that's because you're dividing a change in position divided by a change in time, and so your units end up being something like feet per second. The velocity of, the derivative of position is velocity, as we see here. The derivative of velocity is acceleration, and speed is the absolute value of velocity. Speed is not a vector. Everything else above, meaning displacement, position, velocity, and acceleration, those are vectors, meaning they have a sign and as well as a quantity. They have a direction as well as a magnitude. Speed does not. Speed is always it's just a scalar, and it's either positive or zero. These are a couple of terms, or concepts rather, we're going to see. I think the important ones to keep in mind here, because this looks like a list of rules, which can be overwhelming. The important thing is that direction changes when the velocity changes from positive to negative or negative to positive. So that's one thing we'll want to keep in mind, and that can be tricky. The other thing that can be tricky is when your speed is decreasing and when your speed is increasing. Okay, so it's a little subtle, and I'll do my best to bring out in this example how it makes sense. But essentially, when your velocity and your acceleration have the same sign, that means that your speed is increasing, and on the other hand, if they have opposite sign, your speed is decreasing. So we'll delve into all that through this example. So this says the position, the x-coordinate of a particle moving along a line, is given by the function s of t that we see here. And why don't we, just to give it a little bit more of a direction, let's say it's moving horizontally. So we'll think of our number line as being horizontal. That will allow us to say things like right and left. And we'll think of rightward motion as being a positive movement, and leftward as being negative. We have some units. T is measured in seconds, and S is measured in feet. So we'll keep those in mind as we answer these questions. So it says determine the function v of t that describes the velocity of the particle at any time. So we know that velocity is the derivative of position. So I'm going to say s prime of t is my velocity function, and we use the power rule. So that's 3t squared minus 6t minus 24. So now I have a function for my velocity at any time t. When does the particle stop? The particle will stop whenever your velocity is equal to 0. So let's write that. Okay, whenever the velocity is equal to 0. Okay, so we want to set our velocity equal to 0. So we know that our velocity function is 3t squared minus 6t minus 24. We set that equal to 0. Let's divide everything through by 3. So that gives us 2t minus 8. And you know what? Rather than divide through, let's just factor it out, I think, for reasons that occurred to me now. It's not that big a deal. I'm just thinking ahead a little bit. So we can factor that quadratic. I think it factors to t minus 4 and t plus 2. That looks right. And so then we note that this implies t equals 4. This implies t equals negative 2. But one thing to keep in mind is the whole situation was defined on an interval where time was greater than or equal to 0. So that tells us we don't need that. And so we know at t equals 4, let's put the units in, seconds. T equals 4 seconds. The particle changes direction. The particle stops. Determine the function a of t that describes the acceleration of the particle at any time. Well, the derivative of velocity is acceleration. And so we use the power rule again on our velocity function right here. So that gives us 6t minus 6. Create v of t and a of t number lines. So one thing to keep in mind is that a number line is really just a way of organizing information to help us answer problems beyond that. So I'm going to start here by making a velocity number line. I'm going to have it start at time 0. And what goes on a velocity number line? Well, definitely whenever the velocity is undefined or 0. We found that at 4 seconds, the velocity is 0. So I'm going to put that there. So the other thing you'll want to indicate on the number line is in between when the velocity is 0 and in this case when this whole situation begins, we'll want to know if the velocity is positive or negative. So we pick a representative number in between 0 and 4 and plug it into the velocity. So I'm going to just pick 1. So I'm just going to kind of indicate down here v of 1. Now I don't care what this value is right now. All I care is whether it's positive or negative. So if you go look above, let's plug this 1 into the form of the velocity that I see right here. Okay. The 3 is positive. Right, so I have a positive number times 1 minus 4 is negative, and then 1 plus 2 is positive. A positive times a positive is negative, so velocity is negative, and therefore we indicate that with a negative sign above. And if we plug in a number to the right of 4, like 10, let's see, v of 10. So 3, of course, is still positive. 10 minus 4 is a positive number, and 10 plus 2 is a positive number. A positive times a positive times a positive is positive, so our velocity is positive. Okay, you might, at this point, if you want, just kind of help you make sense of this problem. We're moving rightwards and leftwards in a number line. So a negative velocity means this particle is moving leftward. Moving left, this means moving right. And of course, this means the particle stopped. All right, now let's try our acceleration number line. So do that below. Trying to get it to do straight number line. Let's see. There we go. T, this is A of t. So of course, on this number line, we want to know when the acceleration is 0. That happens if we solve this little equation up here. 6t minus 6 equals 0. You can see there, that means t is 1. And same sort of thing. We're gonna plug in representative numbers to indicate whether the acceleration will be positive or negative. Should put the 0 there. So let's see. Let's do a of a half. A of 1/2. Well, 6 times a half minus 6, that is a negative number, so that's less than 0, so I'm going to put a negative here. And on the other hand, a of, I don't know, 5. 6 times 5 minus 6 is a positive number, so I indicate that there. All right, so I've got our number lines. This will help make sense of many of the problems below. So this question says, when does the particle change direction? Okay, when does the particle change direction? I'm going to indicate here that the particle changes direction when the velocity changes sign. Okay, when the velocity changes sign. So we can see that from our number line above, right? The particle changes direction at t equals 4, and that's because the velocity changes sign from negative to positive. So we're going to say that the particle changes direction okay, since let's just say v of t changes sign from negative to positive, negative to positive. When does the particle speed up? So this is going to be where we have to take a little diversion so I'm just going to indicate speed up. Okay, we're going to come back to this in a second, and then slow down. We'll indicate there. Now, here's the thing. This can be a little tricky. So what I'm going to do is I basically took pictures of these graphs in Delta Math just so we can connect it to how we would do it analytically. So there's my velocity function right there. Okay. Speed is the absolute value of velocity. So notice when you take the absolute value of a graph, you reflect it over the x-axis. So that's what you see there. Okay. Now, the easiest way to answer this question is just look at your speed graph, right? Speeding up whenever your speed function is increasing. It's increasing on this interval there, where again, that's t equals 1. So it's increasing there. It's increasing on that interval. So speeding up are these yellows. Okay, these yellow sections here. And that's just because this is your speed graph. So speeding up just means your speed is increasing, and that just means your speed function is increasing. And that clearly happens on those intervals. On the other hand, this interval here, the speed function is decreasing, so slowing down on this interval. So how do we make sense of that if we're just thinking of the velocity graph, right? Well, let's just note those same intervals. So we noted that below, speeding up happened from 0 to 1 and then 4 to infinity. So let's mark those and then take a few notes. So from 0 to 1, that apparently is when the velocity is, when the particle is speeding up, and this is also when the particle is speeding up. And then that means that this orange section is when the velocity is, the particle is slowing down. So in a nutshell, the way I like to think about it is anytime that that the velocity graph is moving away from 0, right? This is, again, the time axis. Anytime it's moving away from the x-axis, then your particle is speeding up. Okay, so we can see in the yellow sections that's what's happening, right? Your velocity function is moving away from the x-axis. If it's moving away from the x-axis, it's moving away from velocity being 0. So if we just note that, we'll say speeding up, just note it over here. Speeding up, again, that's in yellow. Okay, that's whenever v of t is moving away from 0, meaning the x-axis. Okay, but let's note that what that means is if it's moving away from the x-axis, in the first region here, right? If it's moving away from the x-axis and it's negative, that means that, so our velocity graph is negative, and because acceleration is the derivative of velocity, since the velocity is decreasing, we can say a of t is negative. Notice that a of t and v of t have the same sign. And on this yellow section, same idea, right? V of t is the velocity, which is positive, and our acceleration is positive because it's the derivative of velocity, and clearly it's increasing. So again, same sign. So that's what that rule was earlier in the video. That's how we use it, right? When they have the same sign, we know that the particle is speeding up. And on the other hand, the orange, right, slowing down, that's the orange section. Okay, how do we make sense of that? I'm going to say visually, it's just whenever v of t is moving towards the x-axis. Okay, but again, that means here, right? Notice that the velocity is negative, but it's increasing, meaning its derivative is positive. Okay, they have different signs. So slowing down means your acceleration and your velocity have different signs, and speeding up means they have the same sign. All right, so that was like a little digression just to get us to understand what we need to do here if we don't have the graph in front of us. Speeding up, we're going to say speeding up happens on the intervals where acceleration and velocity have the same sign. So clearly on the intervals 0 to 1, right, because acceleration and velocity are both negative. So maybe I'll just note that. Well, since a of t is positive and v of t is positive. And then also from 4 to infinity. Okay, that's because a of t is oh, I messed up. They're both negative. That's what I meant. Sorry about that. Acceleration and velocity are both negative, whereas on the interval 4 to infinity, they are both positive. Okay, so our answer is 0 to 1 union 4 to infinity. I should just kind of indicate that. And then slowing down is on the interval, well, it's on the interval where they have opposite signs, which is just on the interval 1 to 4. Okay, so 1 to 4. And on the interval 1 to 4, our acceleration is positive, but the velocity is negative. Okay, so they have opposite signs. Okay, displacement. Displacement is a change in position. This is actually a pretty straightforward question. Our displacement is a change in position. On the interval 0 to 5, we just need to find the position at 5 and subtract the position at 0. Let's cheat a little bit just to make the computation a little easier on ourselves. I put the function in Desmos, so let's see what we got here. So there's my function in Desmos. Let's just do s of 5. We get negative 60. Let's do s of 0. We get 10. So we have a displacement of negative 60 minus 10, which is negative 70 And the units, let's just remind ourselves of units up here, right? It's feet. So we're going to say negative 70 feet is our displacement. Find the total distance traveled. So the total distance traveled in this particle by this particle on the interval 0 to 5, what matters in this case is, I should go back to my screen. What matters in this case is we need to know the start. So we need S of 0. We need to know when the particle stopped. We know that stopped when the velocity was 0, which is at 4. And we need to know when it finished, or where it finished. So S of 0, if we just look above, it's it's 10. We also have S of 5, which is negative 60. Let's go ahead and cheat again and get S of 4, negative 70. So we have negative 70 here. So if you were to draw a picture of essentially what's going on, right? We have I already decided it's moving leftward and rightward. At time 0, we're on the number line at 10. So it starts here. It clearly moves leftwards until negative 70. And that happens at time 4. And then it moves back. Right, so this is t equals 0. And then it moves back here and ends up at negative 60 at time 5. So what you care about in this diagram to get total distance is you care about that distance, and then you care about that distance. So we can add those up, or we can understand them by just finding the distance between these two numbers. That distance is clearly 80. That distance is clearly 10. So the total distance traveled would be 90 feet. Okay, everything got counted as positive. And then lastly, we finish with what the velocity of the particle is at a specific time, described as when the acceleration is 12 feet per second squared. So the acceleration, if we look above, was the function 6t minus 6. So we equate that to 12. And we get t equal to 3. So another way to ask this question is, what's the velocity when time equals 3? And our velocity function, remember, was up here. I'm going to use this version that I'm starring just because it's factored. So 3t minus 4t plus 2. So v of 3 equals 3. 3 minus 4, 3 plus 2. So that's 3 times negative 1 times 5, which is negative 15 feet per second. Okay, and we're done. So that was a good rundown, I think, of the key concepts that relate to position, velocity, acceleration as they relate to an introductory calculus class. And we didn't cover everything, and this story gets deeper once you learn about integrals, but this is a good start.